All right, so we have a mic today. Hopefully you can hear me a lot better. We're going to do some 4.5 notes. The learning objectives for these notes are we're going to solve exponential and logarithmic equations. We're going to solve problems involving compound interest. All right, so let's look at some of these properties of equalities. Whenever I have the same base being raised to different exponents, I can go and just set those exponents equal. So for example, if I had the same base here being 2, I can set x equal to 3. Same thing with logs. When I have the same base, I can set those insides equal. So if I had log base 3 and log base 3, I can set 4 equal to x. So let's see how that helps me. Letter A, I have 4 to the x equals 64. So let's think how I could rewrite 64. 4 what? Cubed. So now I have the same base, so x has to equal 3. Okay, letter B. So now I need to make these into the same base. And some of you guys are thinking, oh, I know. Hey, 4 squared is 16. This is wrong. Do not do this. Because now you've taken 4 and made it 4 squared. That is mathematically incorrect. You need to make something that is equivalent. So don't think that you can just throw in anything you want. You have to still make it a mathematical correct statement. So what I always do is I look for the smallest base for both of these guys, which is 4. That will give me, when I raise to a power, both 16 or 4. Well, I know 4 squared is 16. That is exactly the same. I didn't change anything. I didn't just throw something extra in there. 4 squared is 16. So now I can leave this guy over here, x plus 1. So now that I have the same base, I can set these exponents equal. Subtract over the x, and I get out 1. Okay, letter C. Well, what's the base going on if you don't see it? This is base 10 whenever it's not written in. So since I have the same base, I can set the insides equal. So x is going to be 2. So when you have a variable in the exponent that you want to solve for, so whenever it's in the exponent like this right here, so I want to solve for an x, but it's in the exponent, then what we're going to need to do is either ln or log both sides of the equation. This is only after you have isolated the base and exponent. So what does that mean to isolate? It means get this part by itself, then you get to ln or log. So what do I need to do first here? Well, I'm going to have to subtract over the 4. That didn't come out quite right. Now that I have the part that has the variable in it isolated, now I can log or ln both sides. I prefer to ln. And why did I do that? Because now I can use my ln rule that says when I have an exponent, I can bring it down in front. So now 5x is no longer up in the exponent, and I can solve for x. So what do I need to do to solve for this x? I need to divide by the 5 and the ln of 3 on both sides. Yikes, look at this next one. I've got variables up in the exponents everywhere. What should I do? Oh, I know. Let's ln both sides. Let's just see what happens. Because this one's isolated, there's no plus or minus going on. This one's isolated. I don't have any plus anything like that going on at the end. So I've got them isolated. So I'm going to ln both sides. Now that I've ln both sides, I can bring those variables, or the exponents, down in front. Make sure you use parentheses when you bring this guy down so the whole thing is multiplied by ln of 5, not just the x. Okay, now I've got an x in a couple different places. I've got an x here and an x here, and I know I need to get all my x's on the same side. So I'm going to go ahead and distribute on the left. And now I can add over x ln of 5. And if you notice, I went ahead and made this part right here into a fraction so I could see what x is multiplied by. So now I get to pull out the x. And then divide. This is such a beautiful answer, isn't it? Just kidding. And that looks good. If you want to try to reduce it or make it more simplified, that's great, but I will accept that answer. All right, this next one I feel is one of the hardest ones to think about. So the first thing you actually need to do is multiply both sides by e to the x. And I know you're thinking, how would I ever have known that? Well, you wouldn't have, and that's why I'm showing you how to do it now. So we're going to multiply both sides by e to the x, and let's see why. Well, this guy would become e to the 0, which is just 1. So now I'm just going to put it in standard form. That's why we multiplied by e to the x. So we could get it to look something like this. Still looks a little crazy, right? All we're going to do is the AC method on this. So we're going to find two things that multiply to negative 12 and add to the 1. And I got 4 and negative 3. So I'm going to write this as e to the x now because it was squared. Think of like if you had x squared, then you'd write it as x. Okay. So I have e to the x minus 4 times e to the x plus 3 equals 0. Again, think if I had something like this. And all you're doing instead of writing the x is making it e to the x. Okay, now that we've got that far, we're going to set each of these equal to 0. So e to the x equaling negative 4, how do I solve for that? Well, we're going to have to ln both sides. Now I can bring the x down in front. And let's see how many of you remember what is the ln of e. Hopefully you said it is 1. So I know x is just the ln of 4 here. Let's look over at this other guy, e to the x equals -3. Is that even possible? Think about what the graph of e to the x looks like. Can you ever get an output that is negative? So this is not possible. So the only solution that you have that will work is ln of 4. Okay, let's try another one like that, but we didn't have to multiply by e to the x this time. I kind of gave you a hard one so that this one will seem a little bit easier. Now we've already got it in standard form. So again, think of this as x squared, kind of like having e to the x squared minus e to the x minus 6. It's kind of like saying x squared minus x minus 6. So I want to factor this. So let's use the AC method if possible. So let's see, I got -3 and 2. So just like if I had this guy, I'd write x minus 3 and x plus 2. I'm going to do the same thing, except for I'm going to use e to the x instead of x. Whoops. I said x and then I put it in there. There. Better. So now set each of those factors equal to 0. That one was a plus 2. I'm just all over the place right now. Okay. And solve. And I got the ln of 3. See what you guys got. All right, let's try this next one. Some of you flip the page and go, whoa! All right, don't freak out. It's not that bad, I promise. So the first thing we want to do is set it equal to 0. So I'm going to subtract over the 2 times the 10 to the x. Now, what's the first step that we always learn to do when factoring? That's to find that GCF, which is 10 to the x in this case. So I pull out my 10 to the x from all of them, and I'm left with x squared minus x minus 2. Well, I can factor x squared minus x minus 2 using the AC method. And set each of those factors now equal to 0. Hold on, can you have the ln of 0? Absolutely not. And think back again what the graph of 10 to the x looks like. Probably a little bit steeper even than that. You can never get out 0. Remember, you have the asymptote at y equals 0. So this is not possible. This one would be 2, and this one would be -1. So the only answers or solutions that you can have are 2 and -1. Okay, let's look at this next one. Hopefully you said, yay, they're all the same base. So over on the left-hand side, I'm going to use my property of logs that says when I have the same base being added, I can multiply those together. Now that they're set equal with the same base, I can set the insides equal. Now this becomes not so bad. Alright, but with logs sometimes it can get tricky and we need to check out what's going on. So let's go back to this original and look a little bit further. I know the inside of a log has to be positive. So here x has to be greater than 0. Here x plus 1 has to be greater than 0. And that's just a number, so I don't need to worry about it. Well, solving here, I see x has to be greater than negative 1. So let's go and see if these guys meet our conditions. Negative 5, well, it fails the first one automatically, so I can cross it off. What about 4? Is 4 greater than 0? Yep. Is 4 greater than negative 1? It is. So my answer is 4. Are you hanging in there? Alright, let's do this next one. Kind of have some guidelines for you on what to do when you're solving for logs, and that's the first, isolate that log term. Then you want to rewrite the equation in an exponential form and solve for the variable. So let's look at our first one. When I don't see the base of the log, I know that it is log base 10. Just like if I had ln, I know it's log base e. This one, when you don't see it, it's log base 10. I've got log isolated, so now I can go rewrite it in the exponential form. So let's make sure it checks out. Here I know x minus 4 has to be greater than 0. X has to be greater than 4, and 1004 definitely is greater than 4. Okay, let's do this next one. So the first thing I need to do is get just one ln going on here. And right now I have 2. So we're going to use our ln rules that says I can multiply those 2 when I have addition between the ln's. So multiply those together. And I got x squared plus x minus 2. Well, ln I know is log base e. So now I can rewrite into the exponential form and set it equal to 0. Oh my goodness, what do I do here? Well, let's see if I tried to group, would that work? Are these the same? They are not, so grouping is not going to work here. We get to use the quadratic formula. Alright, so in this case I see my A is 1, my B is 1, and my C is negative 2 minus E. You ready to sing along with me? X equals negative B plus or minus the square root B squared minus 4AC all over 2A. So simplify that down and tell me what these are approximately. You can put all that in your calculator. And this is what I got. So let's go see if they work. Here I know that x minus 1 has to be greater than 0, so x has to be greater than 1. And here x plus 2 has to be greater than 0, so x has to be bigger than negative 2. Did both of these guys work? They did not. So the only one that's my answer is 1.7289. All right, how do I put them together now with the logs when I have a minus in between? Hopefully you said we divide. So now that I've got that log isolated, I only have one log going on, I'm going to rewrite it in exponential form. So this has to be a really big uppercut to get all the way over to the 2. But I get something like this. And I'm going to write that over 1 so I know that I can cross multiply. And I just rewrote 3 squared as 9. Oops. And let's check again and make sure this will work. Positive 1. So is 3 greater than negative 15? Yes. And is it greater than 1? Yes. So there's your answer. You guys are doing awesome. Hang in there. Okay, so we're going to do this next one in our graphing calculator. What I want you to do is go to Y1. And let's go ahead and see, this would be log of x cubed minus 3 log of x. Because remember here I could say that that's log of x cubed subtracted over to equal 0. Now that you're here, go find the zeros. So where does it equal 0 in your graphing calculator? And you can pause me while you go check this. Hopefully at least you guys got those 2, and you have a third one. So that's what they are approximately. So if that was difficult, well, let's see how we could do this by hand. Once I have it set equal to 0, I'm going to rewrite this as log of x squared times log of x minus 3 log of x. So now what could I pull out from both of those? What's the GCF? Well, it's log of x. So now I can set log of x equal to 0. And remember, that's base 10. So 10 to the 0 would equal x, which is 1. That's the one we just found. Now I can set log of x squared minus 3 equal to 0. So let's see. Log of x squared equals 3. So log of x is going to equal plus or minus the square root of 3. Don't forget that plus or minus. So again, this is base 10. So when I pop that up, I can get approximately 2 answers. 10 to the positive cube root of 3 or square root of 3 and 10 to the negative square root of 3. And if you see what those are in your graphing calculator, you're going to get out those decimals that we found. So what about restrictions? Do they all work? The only thing x has to be greater than is 0, and they all are greater than 0. So 1, 10 to the radical 3, and 10 to the negative radical 3 are your solutions. Good job. That was a toughie. All right. So let's visit continuously compounded interest. We had this formula before. Let's do a little bit more with it. So A is going to be the amount total after T years. P is your principal or your initial amount. R is your interest rate. And T is your time in years. So whenever you're dealing with money, this is always in years. If you're not dealing with money, then it can be in something else. So a woman invests $6,500 into an account that pays 6% interest per year compounded continuously. What is the amount after 2 years? So let's first set up our equation. So the amount that she first invests is the $6,500. Since it's continuously, I'm going to use the E formula. My rate is 0.06 and then time T. So on A, it wants me to find after 2 years. And that's approximately $7,328.73. Okay, part B, how long will it take the account to be $8,000? So now I'm going to set 8,000 equal and solve for the time. So divide by your 6,500. Math bracket if you need to. And now since I have a variable up in the exponent, I need to ln both sides. And remember the ln of E is just 1. So now to solve for T, I'm going to divide by 0.06. And this is approximately 3.46 years. Okay, let's do this next one. The velocity of a skydiver t seconds after jumping is given by v of t equals 80 times the 1 minus e to the negative 0.2t. After how many seconds is the velocity 70 feet per second? So let's see. 70 is what I'm looking for. Putting in the 80 times the 1 minus e to the negative 0.2t, I need to now solve for t. And since this isn't in money, they say that t is in seconds. Divide by your 80. I don't need parentheses anymore. Subtract your 1. Divide by your negative. And now we can ln both sides. Divide by my negative 0.2. And I get approximately 10.4, and again, it is in seconds. All right, guys, one more. Whew. You can do it. All right, suppose you're driving your car on a cold winter day, 20 degrees Fahrenheit outside, and the engine overheats. Oh no, at about 220 degrees Fahrenheit. When you park, the engine begins to cool down. The temperature T of the engine, T minutes after you park, satisfies this equation. Solve the equation for big T. All right, so if you remember, ln means log base E. So now I can E both sides. Multiply by your 200. And now add 20. There's part A. Part B says, use this to find the temperature of the engine after 20 minutes. So the big T temperature after 20 minutes, I'm going to plug 20. And for time, since it told me that T is in minutes, I don't have to convert anything. And I get approximately 22.2 degrees Fahrenheit. You did it! All right, have a good night, and I will talk to you tomorrow.